Hey guys, IBM is here to take you to another episode of Learning Physics. This is Physics 9702, Paper 4, and we are solving past paper questions in magnetic fields and electromagnetic induction. The questions are up to 2025. I can't give you the order because I want you to watch the videos with a lot of understanding. So this is part 4, and I want us to go straight to the questions for part 4. So in part 3, I think we stopped on page 15, and in part 4, I want us to start with page 16. Question 7, a sphere of mass 1.0 times 10 to the power of 10 kilograms has a charge of positive 0.27 nanocoulombs. The sphere is in a uniform electric field, that means E is constant, that acts vertically upwards. So E acts, the field acts upwards, and because the charge is positive, because the charge is positive, the positive charge experiences a force in the same direction as the electric field, as shown in the figure below. So we have the side view of this. The force exerted on the sphere by the electric field causes the sphere to remain at a fixed vertical height in a horizontal plane. So it is at a fixed vertical height in a horizontal plane. There is a uniform magnetic field. There is a uniform magnetic field in the region of the electric field. So this is what we call a crossed field. The sphere moves at a speed of 0.78 meters per second in the horizontal plane. The magnetic field causes the sphere to move in a circular path. So the magnetic field causes the sphere to move in a circular path. In other words, the magnetic field now provides the centripetal force as shown in the figure here. So this is a view from above, but remember this is in the horizontal plane. Think of the sphere was already in the horizontal plane, and the electric field was vertical, and the magnetic field was causing it to now move in the horizontal plane but in a circular path. This is just a view from above. Okay. Determine the direction of the uniform magnetic field. So I just added here Fleming's left-hand rule. Assuming this is the view from above as indicated, so the dots are showing that the electric field lines are out of the page. The electric field is out of the page, and we don't use Fleming's left-hand rule on the electric field. We use Fleming's left-hand rule on the magnetic field. So we notice that the particle, assuming the sphere is at this position here, in this position here, it is initially moving at a tangent in that direction. So this is the direction of the particle, and the direction of the particle is represented by a positively charged particle. The first finger of Fleming's left-hand rule points in the same direction as motion of the particle. Then, because it is causing a centripetal force, the force is acting towards the center. So the thumb points towards the center. So this is the direction of the force due to the magnetic field. So if the first finger points, if the second finger points in this direction here for motion, and that is on the for a positively charged particle. If the particle was negative, we would reverse the second finger to point in the opposite direction to that of motion. So if the second finger points in this direction of motion, that is the velocity of the particle, and because this is a circular path, the force is acting towards the center of the circular path. So the centripetal force is towards the center. So the thumb is pointing towards the center. Then according to Fleming's left-hand rule, by all means the first finger must point into the page or onto the page. Therefore, the magnetic field must be into the page. So the question was, determine the direction of the uniform magnetic field. So the magnetic field is going to be onto my page if this was a view from above. But remember, this was a view from above. If you now, if you point onto the page, for a view from above, the finger is going to be pointing downwards. So it means that the uniform magnetic field is downwards, because remember the sphere was in a horizontal plane. Assuming this was a horizontal plane, and then now the sphere is moving in a circular path, but the electric field was vertically upwards, and the sphere is moving in that plane. So the centripetal force is towards the center like this. So if we were to consider this kind of motion, the first thing, the velocity of the particle would be there, the thumb, which represents the force, will be there, and that means the first finger would be pointing downwards. The first finger would be pointing down if you were considering this to be the horizontal plane. It's hard to draw a horizontal plane in 2 dimensions, but initially they told us that the sphere was moving in the horizontal plane. So look at your paper on the table as a horizontal plane, and the sphere is moving on the table, just on the horizontal plane, on a circle, which circle is drawn on the paper on your table. That is in the horizontal plane. But then when we view from above, this is exactly what we see. We make the thumb to point towards the center because the centripetal force acts towards the center. We make uh, the second finger to point in the direction of motion at a particular point, because if it was here, the second finger would point in that direction and the thumb would point in that direction. If it was here, the second finger would point in this direction and the thumb will always point towards the center. So if you use Fleming's left hand rule, maintain the direction of those two hands, you notice that by all means, your first finger is pointing onto your table. The first finger is pointing onto your table. And therefore, if we now look at it in a horizontal plane, that will be downwards. Not down the page, but downwards if the sphere is moving in a horizontal plane. Therefore, determine the direction of the uniform magnetic field. So this is going to be vertically downwards. It's vertically downwards, that is by Fleming's left hand rule. It's vertically downwards. So that one I think I've tried to explain in more details. More explanation can be found in the document with solutions. Roman, to explain why the motion of the sphere in the horizontal plane is circular. So we have mentioned that the magnetic force provides centripetal force. The reason as to why the magnetic force is going to provide centripetal force is because the magnetic force remains constant and it is always perpendicular to the direction of the motion, or perpendicular to the velocity. Therefore, it doesn't change the speed of the motion, but it just changes direction, causing centripetal acceleration. So we can simply say that the magnetic force is constant. The magnetic force is constant. The magnetic force is constant. The magnetic force is constant and always perpendicular. And always perpendicular to the velocity. Of the sphere. And always perpendicular to the velocity of the sphere. So, so the magnetic force does not change the speed. The magnetic force does not change the speed of the sphere, but instead causes centripetal acceleration. So for part one, I know that when you look at my illustration with the Fleming's left-hand rule, it appears as if it is into the page. But if you're holding your page vertically, if you're holding your paper vertically, it appears it is into the page. But then when you now rotate it, when you think of the fact that the sphere is moving in the horizontal plane, then it means the first finger is pointing downwards, vertically downwards, if the sphere is moving in the horizontal plane. Calculate the strength of the uniform electric field. When the sphere remains in the horizontal plane, it's because its weight downwards is equal to the force due to the electric field. So the force due to the electric field is going to be equal to the weight of the sphere. Or let's say the force due to the electric field is given by the charge times the electric field strength, which will be equal to mg. So the electric field strength, E, is going to be mg divided by Q, which is equal to what was the mass? The mass is 1.6 exponent minus 10, G is 9.81, then Q is 0.27 times 10 to the power of minus 9. So this is going to be mass, which is 1.6, 10 to the power of minus 10, G is 9.81, divided by Q, which is 0.27 exponent minus 9. So that is 5.813, which is 5.8 to two significant figures. By considering the magnetic force on the sphere, show that the flux density of the uniform magnetic field is 0.14 teslas. So, by considering magnetic force, since the magnetic force provides the centripetal force, I'll simply say magnetic force equals to the centripetal force. So magnetic force is given by BQV, and centripetal force is given by mv squared over r. So since we want to find B, I'll just make B the subject. B is going to be 1V cancels, so that is mv divided by r times q. By substitution, this is mass was 1.6 times 10 to the power of minus 10. V was, what is V? V is 0.73, the radius is 3.4. V is 0.73, and the radius was 3.4, and the Q is 0.27 times 10 to the power of minus 9. I'll check with my calculator. V is 0.78, not 3. exponent negative 10 divided by 3.4 times 0.27 exponent minus 9. So that is 0.1359. 0.1359 Teslas. The examiner always wants to see the answer which rounds off to what is given for questions which ask you to show that a solenoid of area of cross section 1.6 times 10 to the power of minus 3 meters squared is placed inside a larger solenoid of area of cross section 6.4 times 10 to the power of minus 3 meters squared. So this is a solenoid as shown here. The larger solenoid has 600 tons and is attached to a DC power supply to create a magnetic field. The smaller solenoid has 3000 tons. So the smaller solenoid is not connected to a DC any power supply. Compare the magnetic flux in the two solenoids. So it's like the current in the larger solenoid is the one which induces an e.m.f in the second solenoid because it creates a changing magnetic field if the larger solenoid is closed or the terminals are connected. So compare the magnetic flux in the two solenoids. So we know that magnetic flux is equal to B times A, where B is the magnetic flux density and A is the cross-sectional area. So when placed in the same magnetic field, or if we place these two, if these two are in the same magnetic field, the one with a larger area will have a greater magnetic flux, or more field lines will cross a larger area. Because they said they are placed inside a solenoid, a smaller solenoid of that area is placed inside a larger solenoid of area that the larger solenoid has 600 tons and is attached to a DC power supply to create a magnetic field. The smaller solenoid has 3000 tons. So magnetic flux phi is equal to B times A, which means that the larger surface area implies a larger magnetic flux. So we can say it is less. Magnetic flux is less in the smaller solenoid. It is less in the smaller solenoid, or you can say it is greater in the larger or the bigger solenoid. Okay, because it depends on the area. Then compare the flux linkage in the two solenoids. So flux linkage is equal to NBA. So flux linkage is equal to NBA. For a bigger solenoid, you notice that its cross-sectional area, this was 1.6 and the other one is 6.4. So the area of the bigger solenoid is 4 times the area of the smaller solenoid. Then let's talk about the number of turns. The number of turns of the smaller solenoid, I'll quote NS, is equal to, this is 3000, 6000. So that means 3000 divided by 6000, 600, that is, I think, 5. So the number of turns of the smaller solenoid is 5 times the number of turns of the bigger solenoid. So you notice that the number of turns outweighs the size of the number of turns the effect of the size of the number of turns outweighs the effect of the area, even though the area of the bigger solenoid is 4 times the area of the smaller solenoid. The number of turns of the smaller solenoid is 5 times the number of turns of the bigger solenoid. So the effect of the number of turns outweighs the effect of the area. So from flux linkage equals to NBA, even though the area of the bigger solenoid is 4 times the area of the smaller solenoid, the effect of the number of turns is 5 times the number of turns of the bigger solenoid. Therefore, the one which has the higher number of turns is going to have a larger magnetic flux linkage. Therefore, it is greater in the smaller solenoid. It's greater in the smaller solenoid because its number of turns is 5 times greater than that in the larger solenoid. Or you could say smaller in the larger or the bigger solenoid. Okay, so that is the comparison. State Lenz's law of electromagnetic induction. We have already said that the direction of the induced EMF is such as to produce effects that oppose the change that produced it. So the direction of the induced EMF is always such as to produce effects that oppose the change that produced it. That is Lenz's law. The terminals of the smaller solenoid are connected together. So when we connect them together, now we have a complete loop. Therefore, there can be an induced EMF. The smaller solenoid is then removed. Removing the smaller solenoid is equivalent to changing magnetic flux linkage of the smaller solenoid with the larger solenoid. Therefore, an EMF is going to be induced, which induces a current in the smaller solenoid. And of course, by Lenz's law, the direction of the induced current is such as to prevent removing the solenoid. So with reference to the magnetic fields, explain why a force is needed to remove the smaller solenoid. That is now Lenz's law. So I said removing the smaller solenoid. If we try to move away the smaller solenoid, if this is connected completely to form a complete loop, removing the smaller solenoid is going to cause a change in the magnetic flux linkage between the larger solenoid and the smaller solenoid. That means an EMF is going to be induced in the smaller solenoid because already there is a DC in the larger solenoid. The induced EMF also creates or induces a current in the smaller solenoid, which current also causes a magnetic field around the smaller solenoid. The two fields are now going to interact to create an attractive force. It is going to be an attractive force because in accordance to Lenz's law, as you try to move away the solenoid, the induced EMF is going to be such as it opposes moving away the solenoid. So it is going to cause an attractive force on the smaller solenoid by the larger solenoid. That is in accordance with Lenz's law. So the force is going to prevent removing the smaller solenoid. Okay, so we shall simply say that removing the smaller solenoid causes a change in flux linkage, in the smaller solenoid. in the smaller solenoid, which induces an EMF in the smaller solenoid. Then the induced EMF induces a current in the smaller solenoid. Current in the smaller solenoid, which causes a magnetic field around the smaller solenoid. So the two fields are now going to interact to produce an attractive force, and it is going to be attractive by Lenz's law because the moving the coil away should be prevented according to Lenz's law. So the two fields now interact to create an attractive force on the smaller solenoid. So it means now a force is going to be needed to remove the smaller solenoid because the two fields which have now been created tend to interact to create an attractive force on the smaller solenoid. So work is going to be done to move the solenoid further because it is going to be attracted by the larger solenoid in accordance to Lenz's law. Okay. A hollow probe containing a thin slice of solenoid of semiconducting material is placed in a uniform magnetic field of flux density B. The largest faces of the slice are perpendicular to the magnetic field as shown here. Okay. So the slice is perpendicular to the magnetic field, and also the current is perpendicular to the magnetic field. So that means it is experiencing a force. The thickness x of the slice is 1.8 millimeters. The number density of charge carriers, so this is T. The number density of charge carriers in the conductor, that is small n, is 1.5 times 10 to the power of 16 per meter squared, that is small letter n. A constant current I, 5.4 amperes, passed through the slice between the shaded faces. The whole voltage VH, that is the voltage between the terminals PQ, is recorded. The figure shows the variation with time t of B, that is of the magnetic flux density B. Show that B is equal to 4.0 times 10 to the power of minus 6 teslas, and the magnitude of VH is 5.0. The magnitude of VH is 5.0 volts. Okay. When B is 4.0 teslas, the magnitude of VH is 5.0 volts. So what is VH? VH is given by, we know that VH is BI over NTQ, where it is the thickness, and where it is the thickness, which in this case is X. From the diagram, I think it is X. T is the thickness, which in this case is x, and it is 1.8 millimeters. So I'll just substitute this here. So this is going to be B is 4 times 10 to the power of minus 6 teslas. The current was 5.4 divided by N was 1.5. N was 1.5 times 10 to the power of 6. Then thickness was X, which was 1.80 millimeters. So that is 1.8 times 10 to the power of minus 3. And then Q, these are the number densities that Q, what is Q? Okay, so we are going to assume that these are the charge carriers are the electrons, so the Q is going to be 1.6 times 10 to the power of minus 19 coulombs. So I'll just press my calculator. So you have 4 exponent minus 6 times 5.4 divided by, open brackets, 1.5 exponent 6 divided by 1.8 exponent minus 3 divided by 1.6 exponent minus 19. So that is, or B was 4 times 10 to the power of minus 6. Sorry, this is 16. It is 16, not minus 6. So this is, of course, let me check. I'll just divide by 1 exponent 10. That is 5. Okay, I just left out this one here. So this is 5.0 exactly volts. On the figure, sketch the variation of VH, that is the whole voltage, against T. So VH against, from the graph we notice that VH, from the equation notice that VH is directly proportional to B if the current is constant. So it means the graph of VH is going to take the same shape as that of B, because VH is directly proportional to B. So between t equals 0 to t equals 0.05, VH goes to a maximum value, which is 5.0. So this goes 5.0. 1 to 5.0 should be here. So that should be a straight line. So this is going to be a straight line. Then, remember I said it is varying directly proportional. So between t equals to 0.0502 to 0.04, it remains constant. So this is going to be, let me increase the thickness. So this is going to be a horizontal line. Then between t equals to 0.04 up to 0.05, it becomes, B decreases by half. Remember, VH is directly proportional to B, so VH is also going to decrease to a half. So since it was 5, then it decreases to 2.5. And 2.5 is in the center here. Let me see, 2.5. 2.5 is just 1. So I think, no. Since each box is 0. Each box is 2 divided by 5, which is 0.4. This is 2.4. 2.5 is somewhere here in this box here, around there. So let me change that. So 2.4 is somewhere here. 2.5 is somewhere there. Okay, so it's somewhere there. Remember, this is at this time here, so you can make it better. Then now B remains constant for the rest of the time, so this one also remains constant. So it will be constant along just above 2.4. Somewhere there. Okay. So that is the graph. They are directly proportional. It's not exactly 2.6 because remember each box is 0.4. So 2.4 is 2.5 is very close to 2.4 here. Then next, you can try to be more accurate in drawing that. Then the whole probe in A is replaced with a small flat coil that has 3000 turns. The cross-sectional area of the coil is 3.4 exponent minus 4 meters squared. The plane of the coil is perpendicular to the magnetic field, so we don't need to find the sine part or the cos part. The electromotive force or the e.m.f. E induced between the terminals of the coil is recorded as B varies as shown in the figure 7.2. Show that the magnitude of E at time t equals to 0.01 second is 2 times 10 to the power of minus 4. 0.01 second. 0.01 second here. We're showing that we want to show that the magnitude of E, the magnitude of the induced EMF, at time t equals 0.010 second is 2.0 times 10 to the power of minus 4. Remember, the induced EMF is directly proportional to the rate of change of magnetic flux linkage. So EMF equals the rate of change. Rate of change of magnetic flux linkage, which is N. Because B is changing, I will say N change in B times A divided by T. And the change in B times N change in B over T is the gradient. So this is going to be N times A times the gradient. The gradient at T equals to 0.010 seconds. So this is going to be equal to N is 3000. Cross-sectional area is 3.4 times 10 to the power of minus 4. And the gradient Of course, the gradient is, because it's a straight line, the gradient is going to be 4 minus 0 times 10 to the power of minus 6 divided by 0.02 minus 0. Because it's a straight line, the gradient is the same for every pair of points that I choose. So it is going to be 4.0 times 10 to the power minus 6 minus 0 divided by 0.020 minus 0. I'm just showing this to show that I'm finding the gradient. So this is going to be equal to, so 3000, what's wrong with this? 3000 times 3.4 exponent minus 4, then times, that is 4 exponent minus 6 divided by 0.02. So that is 2.04 times 10 to the power of minus 4, which is, of course, this is in volts, which is approximately 2.0 times 10 to the power of minus 4 volts. On the figure 7.4, sketch the variation of E with the t between t equals to 0 and t equals 0.08 seconds. Of course, we know that E is equal to the rate of change, which is directly proportional to the gradient. So E is directly proportional to the gradient of B against T graph. E is directly proportional to the gradient because E is the rate of change of the magnetic flux linkage. So it is directly proportional to the gradient of the graph of B against T. And for the first part, where the gradient was 4 times 10 to the power of minus 6 divided by 0.02, the e.m.f is 2 times 10 to the power of minus 4. So our graph for the first 0.02 seconds is going to be a horizontal line along 2 times 10 to the power of minus 4. Then, so for this part here, the e.m.f is 2 times 10 to the power of minus 4 volts, because we have seen the gradient. Then the gradient of this part here, I think the gradient here, the gradient there would be 4 minus 2 divided by the time interval is 0.01. Which gradient is this? That is 2 divided by 0.01, that is 200. So the gradient here is 200, yet the gradient here was 4 divided by 0.02. Let me check. 4 divided by 0.02. The gradient is the same. So it means the e.m.f represented between t equals 0.04 to 0.05. The e.m.f is the same because the gradient is the same. So that will also be between that point. The e.m.f is the same because the gradient is the same. But I want you to notice that here the gradient is positive and here the gradient is negative. This side the gradient is negative. Actually it is 2 minus 4, which would be negative 200. So the e.m.f is the same in magnitude but opposite polarity. Here between t equals to 0.02 to 0.04, the gradient is 0. T equals to 0.05 to 0.08, the gradient is 0 because the lines are horizontal. So that is going to be, we have 0 between t equals to 0.02, the gradient is 0. So we have a horizontal line here. And 0.05 to 0.08, we have also a horizontal line here along the x-axis. Then 0.04 to 0.05, we have seen that the gradient is the same as the other one but negative. So here the e.m.f is going to be negative 2. 1, 2, 3, 4, 5. So you can use a ruler to draw a very neat sketch, better than mine. Okay, so the graph will take that shape. Please use a ruler to draw a very beautiful graph. Okay, so E is directly proportional to the gradient, where the gradient is positive. For the EMF could be positive or it could be negative. Where the gradient is negative, the EMF could be positive or negative. So if the gradients are opposite, then the EMF should have opposite polarities. That's why I said this side the gradient is positive. I could say the EMF is positive, but this side the gradient is negative, so the EMF must have an opposite sign. I could also take the positive gradient to represent a negative EMF, and the negative gradient to represent a positive EMF. So that is acceptable. In other words, I would draw another graph which looks like this. I would just change the color. I would also be accepted to draw a graph which is like this, starting from the negative end, going to 0, then 0 this side, then here it would be positive, like that. So that would also be accepted, but I'll just leave 1. Okay, so I want this part to stop there. See you in another part. Bye bye.